Hi everybody, welcome to another video in linear algebra, section 3.2, properties of determinants. On the previous section, we defined a determinant and how to compute it. The standard way is to use cofactor expansion along any row or any column. But then we also learned some nice special case to compute the determinant. One way is that the upper triangular or lower triangular or diagonal matrices determinant equal to the product of the diagonal entries. And we also say that if one row or one column is a linear combination of the other rows or the other columns, then the determinant is equal to 0. Of course, when we write like this, the row is a combination of the row and the column, combination of the columns, respectively. Right. Now we learn more about determinants. In particular, what a row operation will do to a determinant. Right. Now, let A be a square matrix. Once again, determinant only works for a square matrix. Let's see if it is not a square, then what do we have? I'm just going to say it. Determinant, let's say a 2 by 1 matrix, which is not a square. I just want to see what is the error message. Right, invalid dimension, right? So only work for square matrix. If a multiple of one row of A is added to another row to produce matrix B, the determinant will be unchanged. So that will be the same. So when we have, if we use, let's say, we multiply something, let's say K times Ri, add to Rj, and replace to Rj, with that determinant unchanged. Next, if two rows are interchanged, now we're swapping two rows. So rows interchange, we will have negative of the determinant. And what if we multiply a row multiplied by K? Then the determinant will be multiplied by K. Now this is very easy to verify. I'm just going to use a 2 by 2, right? A1. Let's put that using the vector form. Right. Let's see, we want a determinant 2 by 2. This one obviously is what? A1 B2 minus A2 B1. Right? Now, consider the same thing. Now, what we do here is we multiply K into one row. Let's say we multiply K here. Of course, if we use the cofactor expansion, we will base everything on that row. So we have KA1 and then KB1. And then cofactor expansion, of course, and then factor out the K. Yeah, so imagine that if we use a cofactor dimension, for example, like this one, if we expand everything on the first row, we're just going to have the determinant, right? Now, if every entry of the first row multiplied by K, then all of this will be multiplied by K, and therefore the determinant will multiply by K. So if we multiply K into a row or a column, actually in here we just have the row now, in that case, the determinant is multiplied by K, by that number, right? Now let's just compute a 3 by 3 determinant. So it's easy enough. Let's just say there's there's a 0 here, so let's just use the third row, expand along the third row. So we have -1 and then 7 and then 0. As for the sign, positive, negative, positive. The third row would be positive, negative, positive. Right? Now, we write the cofactors. Yeah, just don't write everything on the first, on the last row. So cover this up. What's left is -4 and 2, 8 and -9. Of course, I don't write element on the last row. Next one will be 1 and 2, -2 and -9. Yeah, and then 0. Actually, for 0, it doesn't matter. It's 0 anyway. Right. So I have -1, -4 times -9, -2 times 8, -7, 1 times -9, -2 times -2. Right. So negative, that is 36 minus 16. 36 minus 16, positive 20. And then -9 plus 5, -9, -9 plus 5, -9 plus 5 is -4. And do this, we have 28 minus 20. So this is going to be 8. Now let's check. Right. So I'm glad we check. Right. So that is -9 plus 4, so it's -5. And 35 minus 20 is 15. Right. Yeah. So now, what happens if we have -2 times A? What do you think? Right. So how do we multiply matrices, by the way? Let's just say what -2A is going to be. -2 times the matrix right. So if we multiply -2, when we multiply -2, what do? We multiply -2 to every row or every column. In fact, I'm not going to write that. We just say -2 is multiplied to every row or every column. I mean, into the entry of every row, every column. So, of course, I could just multiply that, but I just said it's -2 multiplied to every row and every column. I mean, multiply to entry on every row and every column. Entry on every row. Right. So we just have 1, -2, -1, -4, 8, and 7. 2, -9, and 0. Right. Why don't we just multiply now and we just keep it like this? Well, The reason I want to keep it like this because we're going to use the properties here. If a row is multiplied by a number, the determinant is multiplied by that number. So in this, we will say, by the way, write like this is a terrible way to write, because what we actually calculate here is the determinant of A. Yeah, so that's, of course, they're not equal. This is a matrix, this is the determinant. All right, now determinant of B. Now, how do we calculate the determinant of B? Of course, we multiply this and evaluate, but that's not the point of this exercise. All right, what we see here is we multiply -2 on every entry on the first row, right? So we're going to have a -2. We do multiply -2 on every entry on the second row also, so this is another -2. And we multiply -2 on every entry on the last column, that's another -2. Each time we multiply a row by a number, we multiply that number into determinant. So we just say determinant of B is equal to -2 times -2 times -2 of determinant of matrix A. Because we multiply -2 on the first row, -2 on the second row, and -3 on the third row. So that gives us a -8 times 15, which is -120. Right, we can check real quick. I will insert a -2 in here. Sorry, that's a terrible way. By the way, if you use TI-83 and you cannot go up and then copy and paste like what I do here, just hit second enter, it would just pull up the last entry. Insert a -2. Right, so that's what we have. Yes, so you see what we have here is another note in the determinant. Note, if an n by n matrix is multiplying by k, then its determinant is multiplying by, the reason I have to write the dimension here, because if there are n rows, that means we multiply that and whatever the constant n times. If there's 4 rows, multiply k to the first row, second, third, and fourth, so there are 4 of them. So essentially we multiply by k to the n in the determinant. So this is another note in the determinant. Yeah. So we don't have to multiply it out and find it, the determinant. If we already have determinant for A, just take in this example, we say determinant of B is equal to -2. This is a 3 by 3 matrix, so it's going to be 3 times -2 cubed determinant of A. In our example, we use that properties here, which is -8 times. Right. Matrix C. There's nothing special about this. Well, at least we see a bunch of zeros. So let's just evaluate along this column. Right. So we say determinant of C equal to, I'm going to write out 0 it doesn't matter. Inside it's going to be 0, and then we have -3, and then 0, and then 0. Right. Now the signs, don't forget the signs: positive, negative, positive, negative, positive, and negative. Right. Now the cofactors, I mean the submatrix, if you will. Yeah, I'm not going to write anything on that column. Right. For first one, it doesn't matter. For 0 here, actually it doesn't matter. And 0 here, it doesn't matter. What is the minor or the cofactor? It's going to 0 anyway. Yeah. But for -3, let's just go over the row in the column of -3. What do we have here? 1, -4, and 2, -2, 8, and -9, -1, 7, and 0. Of course, we can find the determinant here. But notice that I make this example a little special so I don't have to do, just so that that's just determinant. That's just A, right? The same thing. If you compare that to the matrix A, this is the same thing. And we have 2 bars, so this is determinant of A. And now we have negative times negative, so that's just 3 times determinant of A. Determinant of A is 15. Yeah. So there's no things, no special here. It's just that when we evaluate determinant, we're going to pick the one with the most 0, any row, any column that has the most 0 in it. Right. Just going to evaluate very quickly the determinant. Determinant is the first option. So it's nothing special here, just a definition of determinant, and recognize that we already did determinant of that 3 by 3 matrix. Right, something more interesting. How about this? Right, first, if the star is any number, we cannot just expand this out and write in the cofactor expansion. It takes a lot of work, and besides we don't know what the numbers are, so there must be something to it, and definitely is. This is just a review showing that in here we have an upper triangular matrix, so we just equal to a product of the diagonal entries. If it is a lower triangular matrix, it is also the product of diagonal entries. If it is equal to diagonal matrix, also the product of diagonal entry. So here I just said 2 times 4 times 1 times 3, 6, 8 times 3, 24, that's 4 factorial. Right, and I just write a little note here. This is an upper triangular matrix. Is an upper therefore the determinant is the product of the diagonal entry. Doesn't matter what the star is, because it is upper triangular matrix. Right. So we have some special note about determinant. This from the previous section, and this note in this section. Of course, I'm sorry, this in this section. The theorem. Right. Now, this one, if we have to do it, this will be very easy, right? Because they are 1 to 0, will be obvious. So, but instead of doing that, I just want to write something a little more concept. So, what did we have earlier? Sorry. If two rows are interchanged, then the determinant is going to be opposite to the previous one. So now I will write, let's just do it like this. Determinant of this, sorry, now if we just interchange the row and column, interchange the first two rows. Now if we interchange the first two rows, the determinant is going to be opposite. Of determinant of this matrix, and this one is the diagonal matrix. So just negative 3, 2, negative 1. Yeah. So this is diagonal matrix, similar to upper triangular matrix or lower triangular matrix. Determinant is just a product of the diagonal entries. So that's pretty much all the special properties that we need to watch out for. Other than the one thing that we say would be a little less obvious to look for is if one row is the linear combination of the other row. That would be difficult to look for. But other than that, the obvious case is what we note. The first one is triangle, upper triangular, lower triangular, and diagonal matrix. So upper triangular, lower triangular, or diagonal. We know that determinant is equal to a product of diagonal entries. That's the first one. Next we have just the last one, row interchange. We turn the determinant into the opposite to that. So row interchange, what do we say? Just turn into opposite values of the determinant. And then the next, multiply by k. To one row. Determinant equal k times the original. So we will have k times determinant of the original matrix. If we multiply by the whole matrix, then that will be multiply by k to the n. So determinant of kn, k times a, is equal to k to the n power determinant of a. Right. So that's what we have so far. Of course, the first one is ladder. We usually don't see that. We usually don't use that because it's not very easy to see. Right. So those are what we have for determinants. The important things about determinant. Now, more properties of determinant. It says that if A is a square matrix reduced to an echelon form matrix U, determinant of A is equal to -1 times the product of the pivots, meaning the product of diagonal entries, times -1, where -1 to the R, where R is the number of row interchange, because every time we do a row interchange, we turn the determinant to opposite. So we have to do that. By the way, of course, using the row operation to evaluate determinant is not the most efficient way. The most efficient way is just use the cofactor expansion along any row, any column. Now, this theorem is important. A square matrix is invertible if and only if determinant not equal to 0. Sorry, I had to pause the video to look for the note in the previous section. So now, let's go to page 57, or the first page of section 2.3. We say that if A is a square matrix and if it is invertible, then we have all of those equivalent properties. Now add one more to that list. If determinant is not equal to 0, then all of these properties will be there. Once again, if A is the square matrix and we have determinant not equal to 0, we will have all of these properties. So that will be one more, so 13 of them. Determinant not equal to 0. That equivalent to all of this. Right. Now back to what we have here. And then with that, we say if the column of A are linearly dependent or the row are linearly independent, because we do say that the columns of A form a linearly independent set. In that case, if that is the case, if the columns are linearly dependent, notice that linearly dependent here, meaning one column is the linear combination of the other columns, or one row is the linear combination of the other row, then the determinant is equal to 0. Right. Now, like I said, that is usually kind of difficult to see. Like this example, when we look at this and we say, what's so special about that? Of course, I won't be able to tell you anything, but let's consider that little hint. If we replace row 3 by 2 times row 1 plus row 3, I'm just going to do that by hand. 2 times row 1 plus row 3 store into row 3. In that case, row 1, 2, and 4 will stay the same, so I'm just going to copy that, so it'll be less thing to worry about. Right, row 1, 2, and 4 will stay the same because we only change row 3 here. Right, now 2 times row 1, 6 minus 6. 2 times -1, -2. -2 plus 7, so -5. 2 times 2 is 4. minus 7 minus 3 2 times negative 5 negative 10 plus 4 is negative 6. What's so special about that? Oh, I see now. So when we do that, notice that these two rows are the same. Do we? Because I do that differently. 2 times negative 2 that should be plus 5. Actually, they do equal, right? So these two rows are equal. So that means is these two rows are not linearly independent. So because they are the same, that means they are linearly dependent. I just spelled that. And if we have two rows that are linearly dependent, then determinant is equal to 0. So we don't have to do anything. And then you say, wait a minute, we did use this row operation. Does that change the determinant? It does not, because at the beginning of section 3.2 we say that if a multiple of one row of A added to another row and replaced, so pretty much when we do this, the determinant will be the same. So that's the only operation that will not change the determinant. So in that case, it's going to still, when we do this, determinant is still unchanged, but equal to 0. So determinant of this matrix is equal to 0. So determinant of that matrix is equal to 0. Because this row operation does not change anything. The other row operation will change the determinant. This one does not. Right. And one thing you probably expect already, because the properties, like I said, the 12 properties we have earlier, determinant of a matrix transpose is equal to determinant of a matrix. That's why when we evaluate the matrix, we can use cofactor expansion along any row or any column, because we can transpose them row become column. So row or column, it doesn't matter. And last, we have this. If A and B are n by n matrices, then determinant of A times B is equal to determinant of A times determinant of B. Of course, if the matrices are square matrices. Right? Determinant of the product is equal to the product of the determinants. Right. Now let A equal to that. Let's find determinant of A inverse. So how do we do that? Let's first, A is upper triangular. So let's find determinant of A. Right? So we say since A is upper triangular, determinant of A is equal to the product of the diagonal entry. That's why the star here doesn't matter. That is negative 10. Now, to find determinant of A inverse, we will use this trick. By definition, we have A times A inverse is equal to the identity matrix. Right? Definition of inverse matrices. In that case, we use the properties that we just have. Actually, we just take determinant on both sides. Now we use the properties of the one we just have. Determinant of A and determinant of A, determinant of A times A inverse. We can split that using the properties we have here. So that equal to determinant of A times determinant of the A inverse. Now, what is determinant of identity matrix? So what's so special about identity matrix? Well, identity matrix is the diagonal matrix whose diagonal entries are 1. So this is identity matrix. We only worry about 3 by 3 here. So that's going to be equal to 1. Right, so we continue. We have determinant of A, which is -10. And determinant of A inverse is equal to 1. I mean, -10 times determinant of A inverse is 1. So determinant of A inverse equal to 1 over -10, which is -10, which is -1 over 10. Right. Of course, we don't have to do that every single time. We could just say that we just divide determinant of A in here. So from this implies that determinant of A inverse is 1 over determinant of A. Yeah, so more properties of determinant. Determinant of the inverse is 1 over determinant of the matrix. And or we can just use that directly. Calculate determinant of 8 and then 1 over that will be the answer. Alright, this example determine if the following vectors are linearly independent. Well, we just pretty much put everything in that. We say if it is linearly independent, then the determinant is not going to be equal to 0. So we just pretty much find determinant. So we just say determinant of that matrix notice that these are vectors. So v1, v2, and v3 are vectors. Right, now if this determinant not equal to 0, therefore it is invertible. And all the properties given by that theorem, we have like 12 all the things we can say about when determinant not equal to 0. When it's invertible, there's a lot of things we can say about that, including the rows are or the vectors or the columns are linearly independent. So pretty much we just find the determinant. I'm just going to use a calculator here because by now we should know how to do this. Of course, the default way is always cofactor expansion along any row or any column. Right. So 5, -3, 2, -7, 3. Right. Just find determinant. And determinant equal to 0. That means they are not invertible. That means the columns are linearly dependent. So we say if determinant not equal to 0, then we have all these properties. But since when we find determinant of v1, v2, I don't want to write that again. When we do if it is not equal to 0, we have all of those properties. But since we do not have that, since the determinant of this equal to 0, it is just linearly dependent. Right. So it's simple enough. Just when we have the columns, put that in the matrix and find determinant. It's not a very usual way to do this. Let's say if we have two vectors, we cannot really put into a determinant, right? Yeah. So if we have the same number of vectors as we have the number of vectors that make into a square, then we can use determinant to test to see if the vectors are linearly independent. But otherwise, we have to use the reduced to echelon form, and of course that already discussed in section 2.3. Right. But this is where we stop at the end of section 3.2. Thank you for watching. As always, see you in another video in linear algebra.